means perfect curing is achieved. K2 is the environmental variable, let's say. So it's a moderate environment. The surface concentration is 358 ppm. That's the UK value. I don't know what the surface concentration here is. So you can approximate based on whether it's Bangalore city or Mangalore or in the middle of the sea. Binding capacity is assumed very similar to surface concentration because then they will cancel each other and make things easier for you. You can estimate that based on the calcium and the sodium contents of your concrete. But that needs further research. We haven't agreed on anything yet. T naught represents the time in which the concrete will be shielded, protected. So if your exposure time is 28 days, then that's what it should be. So you made the concrete, 28 days you protected the concrete and you removed everything. That is your time 0. Okay. Also the time at which you measured your diffusion coefficient. So if you cast the concrete, you waited 28 days to measure the diffusion coefficient, that's 28 days. In this case I'm saying it should be 1 year because I prefer everything to be long term. Durability should be a long term goal, not a short term thing. So try to fit that equation into Excel and see how it works for you. And develop a graph which looks like this. So I would want you guys to give me if you put an equal to sign in Excel and then you put a function, whatever function you want. So for square root is sqrt and then in brackets whatever you want to enter. So the function will call everything then. So to the power is, I think it's exp, or there's a symbol like that.
Yeah.
You can use either.
Yeah.
Yeah, just remember, because you're putting everything same, so if you're putting time in years, convert the diffusion coefficient to meters squared per second into meters squared per year, or the other way around. Make sure everything is in, or else. Just to give you an idea of how C, the other is T, or T starting and then XT. And I'll enter the equation here, one of them. Okay, that's all the equation. And then see when you click it, you drag the box down, so it will apply the equation to all cells, as many cells as well. Sir, can you take the data? Zero refers to the time at which you expose the sample or the time at which you test the concrete. So we now need to be testing the concrete after. So blended cements means it needs that calcium to make the other things react, so it'll have the lowest. So binding capacity will be lowest for blended cements. Higher the proportion of blending, lower the calcium hydroxide content. Carbonation will also affect other calcium and sodium phases, and that's when the cracking and everything happens. It's better not to rely on them because it's a very destructive failure then. So try changing the binding capacity to 30 and see what happens to your graph. So keep the graph in blue color, which is your reference. Any change, just put a different color and then use a legend to say what change you have made. It is important that you play with the variables so that you know how confident you are with the graphs. Second, how sensitive each variable is. The more sensitive the variable, you will need to pay more attention in getting that variable quantified. In this equation, without looking, I can say your diffusivity, but more your binding capacity will be extremely sensitive. So find a way of defining the binding capacity. By that means join the Rylem crowd. They haven't defined it yet. So change it to 30 ppm, A equal to 30 ppm, and see what happens. And then afterwards change, as a new change the diffusion coefficient to maybe half, keeping the 30 ppm. See the difference. Because Andreas contributed to the report, So this is his version, whereas the final report is the version of everybody. Okay. So my suggestion will be go back and try the final technical report. It might happen one day. So how did you guys get the? Happy to lift your head from the mathematical genius of an Excel file. So I suggested that you look at a diffusion coefficient of 1 and the binding capacity of 15. And this represents a typical concrete used using Portland cement. Okay, so it's 100% Portland cement. Okay, if you want sorry, that's wrong. So the higher binding capacity represent that concrete has a lot of calcium elements in it. So this is your 100% PC. Okay, and you can see clearly that this is a good concrete for that environment. And if you look at the standards, if you look at the European standards, you will see they tend to prefer more of Portland cement for the carbonation environment than high volume substitutions. Okay. You know, we'll look at the European standards. On the right side of it, it says type of cements or type of binders allowed. They tend to prefer Portland cement for carbonation. Now, let's say you have to use a high volume replacement cement for other reasons, for other durability issues, chlorides or anything else, and you will then have your binding capacity reduced. Okay. So for comparison, I wanted you guys to start at D is equal to 1 and A is equal to 15. Okay. That means you're using a different cement but with a comparable diffusivity. That highly likely means from here you've increased the water binder ratio. Okay. Binding is reduced because your binder has now changed. Diffusivity naturally should have come down if you use a high volume replacement. It has increased because you've changed one of the other factors. Maybe you've used more water. But naturally you get lower diffusivity if you use a high volume replacement material. So let's say this is your 75% GGBS plus PC. Okay, so this is that. So you've got a reduction in diffusivity. Because of the GGBS part of it, you would have got a reduction in binding capacity, which means that concrete is not bad in that environment. You know it's not great, but it's not bad. That logic is your decision. Because you're not, the game is carbonation sometimes, the game is carbonation plus chlorides plus a number of other things. So you need to make a balancing decision. You can say, by reducing the diffusivity with the supplementary binder, the flow is slower, therefore I can get an extended service life compared to using pure Portland cement. Okay, so this is how you take multi-part decisions. A decision based on carbonation, decision based on chlorides, decision based on other things. Ultimately, your decision is to see if this is 50 years and this is 100, where should I put the steel? That's the bottom line question, okay? It's the service life. You should put your steel above that XC. XC represents the depth to which it will carbonate, okay? So if I plot it back, if I'm going to use that cement, the cover depth should be this or more. Okay. And if I'm going to use that cement, the cover depth should be a little bit more. And if I'm using that, it'll be a lot more. Okay. And that should tell you the minimum cover depth. So if you can take an output from here, you can say this is C minimum. Okay. And like that, you can create C minimum for every exposure environment. And whichever is the maximum of that minimum, you can say that should do the job. as far as I'm concerned, there are three things you're getting from here, okay? You're getting a performance measure out of this method. You are defining all the variables to who may come next, because they're looking at your calculation to say, you got a diffusivity of this, which is a performance measure. You counted the binding capacity correct, or maybe not correct in their terms, but at least you quantified it. And they can see what way the prediction should have gone. And that's the best gift that you can give to them. It's almost like a car, when you buy a car and somebody's saying, your mileage is this, and it has been this. So you are transferring the performance data to the next person who is looking after the structure. Highly likely you'll be transferring the data to the client or their own asset management body and tell, this is what I'm expecting. Can you perform a test 20 years, see where you're going? That difference might be your exposure environment. You use 358 ppm CO2. What's the CO2 around us here? This room, I'm sure, will be higher, but what's in Mangalore, what's in Bangalore, what's in Delhi? And what's in an industrial environment? So it will be different.
It's quite high.
So you can create more graphs with different changes. And you can say, for an industrial environment, we prefer the cover to be raised, certain value. The next question is climate change. We're expecting